Okay, so in the last part of our lesson, we consider some basic R code that we can use, for example, to play a little bit with the value at risk and the expected shortfall. Now, as you will see, I'm using RStudio in order to play a little bit with the code, and I'm providing the notebook that I'm using with some extra comments. So in this short video, I will go quite quickly through the different steps because I want to actually focus more on the interpretation of the results and on some specific parts of the code. I will not consider all the different lines of code. This is something that I leave to you. In any case, if something is not clear, you know how to reach me. Together with the many different packages that we will use through the course, like the EVER package for extreme value theory, like the TS package for time series and so on, there is one package which is quite important to us, which is the quant mode package. This is one of the many packages that in R can be used to acquire real data, to acquire financial data. And since it is very simple to use and you can find plenty of extra resources about the use of this package, this is the package I have chosen for our course. So if it is not in your R installation, please install it because it's very, very important. Also for the different units of this course, because we will always try to play with actual data, with real data, because for sure we will consider some, if you want, in vitro situations, some situations in which we can control for everything, for example, to understand a little bit the theoretical properties of a model, like the Merton's model for what concerns credit risk. But what is really fundamental to be a good risk manager is to be able to play with actual data. And actual data always have a lot of problems. So we will try to tackle these problems together. So please install the package and try to familiarize a little bit with that. In the notebook, you find a link and other resources are available if you do the, let's say, the one of the most common things to do nowadays, that is to say, if you Google something about the package. Okay, this is the RStudio notebook that I'm sharing with you. So in the course materials, you find the notebook and you can replicate all the things that I'm doing here. So as I told you, in this notebook, we will start using the Quant Mode library that allows us to download a lot of financial data. And so if the library is not already installed in your system, please do that. After that, we can just invoke the library, so library Quant Mode. And let's say that we want to consider the behavior of the shares of the stocks by Apple. So what we do, we can download the behavior of the Apple stock using quant mode, and let's say that we download all the data from January the 1st, 2016 until a couple of days ago, so April the 20th, 2020. Okay? Now, most of the data sets, most of the time series are available via Yahoo, so we can give Yahoo as a source. Other sources are available, like Google and many others. What I suggest is that you have a look at the help of the quant mode library. After that, for us, our stock is nothing more than the values included In Apple, notice that we can obtain different values. We can get the so-called adjusted value, the opening, the closing, and so on. So we use the adjusted value. Those will be our stock value. We can have a very simple time series plot of our series to see a little bit the behavior of the stock. And most importantly, we can compute the returns of the stock. Those will be the object of our analysis when we want, for example, to compute the value at risk and the expected shortfall. Now, as I told you, we have the point of view of risk managers. So for us, losses are positive and profits are negative. That's why in computing the log returns, after that, I apply the minus sign, okay? Because I want losses to be positive and profits to be negative. So the positive returns, what we usually consider the positive returns, are now negative and vice versa, okay? And again, we can have a chart series of this plot. So let's just run this part of the code. What we get are exactly these graphs. So this is the first graph. It's the behavior of the stock. You see over time, and we see that there was a clear increase in the value of the stock, naturally with periods in which the value went down, but all in all, there is a quite clear increase in the stock. After that, we can compute the returns. Remember that now the positive part are actually the losses and the negative part are the actual returns in terms of positive and positive increase in the value of the stock. But for us, it's the negative part. This is a quite typical plot of the time series of returns of a stock. Later on in the course, we will observe nice phenomena in this plot. For example, you see that there are periods in which the oscillations are smaller, like here. These are the periods of low volatility. There are periods in which the oscillations are much larger. These are the periods of high volatility. And you see that periods of high volatility are followed by periods of low volatility and vice versa. And this is a phenomenon that we will tend to call volatility clustering. So the fact that we observe clusters of volatility behaviors. Okay, so these are the starting point of our analysis. Now, assume that we want to compute the value at risk of the losses and the returns, and we want to start from these empirical data. Now, from a statistical point of view, we know that the value at risk is nothing more than a quantile. So in R, we can just use the quantile function that computes the empirical quantiles out of a series of data. So if we are interested in the 95% value at risk, it's just quantile, stock loss 0.95, and we give the usual option for what concerns the removal of the not available information. And for the 99% value at risk, again, it's exactly the same syntax. The only difference is that we say 0.99 instead of 0.95. So if we compute these quantities again, you see that the 95% value at risk is 0.02 and friends. And for what concerns the 99% or the 0.99 VaR, this is 0.0538 and so on. So what does it mean? It means that if I consider all the possible movements in the value of the Apple stock, then I can expect that 95% of all the variations will be smaller than 0.025. In terms of the original data, it means that a decrease in the value of my stock, which is larger in absolute terms of 2.5%, will happen only in 5% of the situations. And for what concerns the 99% vet risk, this value is now 5.38%. So it means that only in 1% of the days of the situations I should and I could expect losses above, in absolute terms, 5.38, or that is to say losses below minus 5.38%. If you want, not particularly useful at this stage, but in any case, a very simple heuristic that I always suggest to use is to quickly check how many observations actually lie above a given value at risk threshold. So, for example, if we consider all the values that lie above the 99% value at risk, we would expect only 1% of the observations to be above. And if we do that empirically, what can we do? If we use the function which, the function which will find in our array stock loss what are the values that are actually above the 99% valid risk, which is 0.0538 and so on. We find out that these are the values. So these are actually the coordinates of the points. So if you want observation number 17, number 18, 716, so if we want, we can go there and try to understand more, check for what happened on that particular day and so on. So these are common things to do in analyzing a financial time series. But for us, it's just sufficient to see that if I consider the length of this vector over the total number of observations that I'm considering in my time series, this is exactly 1%. Okay, so not exactly, sorry, it's more or less 1%, which is in line with our expectations. Now, in this specific situation is not particularly relevant because we are using already the quantile function, and it's obvious that in terms of the empirical quantile, we have that the condition of having only 1% of the exceptions is satisfied. But if, for example, you have a theoretical valid risk, as we shall see in a moment with the normal distribution, then in that situation it's always very nice to check if your valid risk also satisfies very quickly, heuristically, empirically, the requirements in terms of exceedance probability. If we want, we can generate a new plot of our loss and return distribution, and we can add two lines to represent the 95 and the 99% valid risk. And this is what we get. So this is what we observe, and you see that looking at the time series of the losses and the returns, I have a certain number of observations that are above the 95% valid risk, and I can expect these observations to represent 5% of the total number of the observations. For what concerns the 99% valid risk, this is the blue line, and I can expect 1% of the observations to lie above, and these observations are exactly the observations that I have already identified before. Again, if I want, I can go there and try to understand, for example, what happened in this particular day or in this particular day. Now, if I want to compute the expected shortfall is nothing more than this conditional mean of all the losses above a given VaR level. So I can just compute the mean of all the stock losses above the VaR level. Okay, this is one of the many ways in which we can actually write down the expected shortfall, and one of the many ways in which in R we can compute this. So you will notice that in all my codes, I always stick to the simplest version, the most intuitive one. Now, you can be very, very fancy if you want, but at least at the very beginning, I think it is very important to be a little bit pedantic and follow all the different steps. Okay, so I can compute my stuff, and these are my expected shortfalls. Now, For mathematicians like you, it is trivial to observe that at a given alpha level, the expected shortfall will always be larger than the corresponding valid risk. In reality, it can also be exactly the same as valid risk if there is a degenerate mass on the valid risk itself. So, for example, if I have a distribution such that 95% of the observations are smaller than the valid risk, and the valid risk itself represents 5% in terms of probability, so all the mass is concentrated on the valid risk. In that specific situation, the 95% expected shortfall will coincide with the valid risk, but not in general. In general, the expected shortfall given an alpha level is always larger than the corresponding value at risk. Now, what happens if we want to compute valid risk and expected shortfall under normality? We will see that, unfortunately, the normality assumption is omnipresent in risk management and often also a dangerous assumption. Yet, it is still used and abused a lot. Now, under the normal distribution, both the valid risk and the expected shortfall have explicit functional representation. So we have an explicit formula for the computation of the valid risk. The VaR alpha, so the alpha valid risk under the normality assumption, is just mu plus sigma 5 to the minus 1 at the alpha level. Now, mu is the mean of my normal distribution, it can be 0 or any other value. Sigma is the standard deviation of the normal distribution. And phi to the minus 1 is the quantile function of a standard normal distribution. Okay? This quantity can be computed in R using the different P norm, Q norm, D norm functions, or if you have the very old-fashioned yet useful normal tables, you can compute the quantile directly from the table. Now, you see that if you consider this formula, and this is the formula for the valid risk at the alpha level under the normality assumption, under a normal distribution, now it should not be a problem to observe that in this situation, the valid risk is actually subadditive. Because take, for example, two different valid risks for two different assets following two different normal distributions. You will have a mu1 and a mu2 for the two assets, a sigma 1 and a sigma 2, but the phi to the minus 1 alpha part is the same because obviously the alpha level is fixed for the two assets, say 95% or 99%. Now, sum the two valid risk, you will see that you can collect the mu's, but if I sum two normally distributed random variables, I know that the mean of the sum is just the sum of the means. For what concerns the standard deviation, it is not important if they are independent or dependent, because I know that the standard deviation is a coherent risk measure. So if I consider the standard deviation of our portfolio made of the combination of these two assets, then the standard deviation will always be smaller than equal to the sum of the standard deviations. And given that, I immediately obtain that the valid risk is subadditive under normality. Please do that, write it down, but it's an extremely simple exercise. For what concerns the expected shortfall, this is the functional form, so this is our formula. You already know all the quantities apart from this phi here that represents the density of our normal. Now, if I want to compute, for example, the 95% valid risk of a normally distributed random variable with mean 0 and standard deviation 2, I can use the Q norm function, so the quantile function of a standard normal, in which I then also give information about the mean and the standard deviation. So Q norm 0.95, 95% valid risk with mean 0 and standard deviation 2. If you omit the information about the mean and the standard deviation, then Q norm assumes that you are working actually with the standard normal, so mean 0 and standard deviation 1. Okay, now what I want to show you is that the normality assumption, as it would be evident in the lessons on extreme value theory, can be a very tricky assumption very dangerous assumption in risk management, because while it is true that it simplifies a lot our computations, and we also gain nice properties like the coherence of the valid risk, it is not verified in data. So it is like you use a model to describe reality, but you want to force reality to follow your model. It is like you have a model that predicts something, and since that something does not happen because your model is actually wrong, you essentially complain by saying that the problem is not the model, but it's reality that does not follow your model, which is unfortunately very common in risk management. Now, let's use, for example, the Dow Jones Industrial Average returns over the last 30 years, okay? Now, as before, I can easily get my data. I can compute the stock returns as before. Then I create a variable losses that contains the stock returns with a changed sign. Now, if you want, this syntax is a little bit redundant. We could have done everything in just one line as before, but as I told you, I like to show you different ways, and sometimes I know completely that I'm a little bit pedantic. Now, what I do, I also compute the mean of the losses, the standard deviation of the losses, and all the number of observations that I have in my data set. Why do I do that? Because then I want to show you that if I assume that my log returns are actually normally distributed, I can always generate a certain number of normally distributed random variables with the same mean m and the same standard deviation s, which is what I'm doing here. And I can compare these random variables that I have generated with the same mean and the same standard deviation, and so the same variance, with the actual observations that are the ones that I'm considering here. Now, if I do that, I find something quite nice immediately. So first of all, if you want, I can immediately have a look here at the mean. I see that the mean is minus 0.0003, so it's very close to 0, so in a sense it can be safely set to 0, the mean of my losses and return. And in fact, we see that on a daily basis, so if we consider daily observations as we are doing, typically the mean can be safely put to 0, also from an empirical point of view. So it's never a real 0, but you see we are considering 0.0003, so it's small enough. And it's negative because we are considering the losses and the profits. So actually the real mean in terms of returns and losses is a positive. So there is, on the market, we tend to earn a little bit more than what we lose. That's why the mean is positive, or for us, that we are risk managers, negative. So in a sense, you can also connect these to all the theories of endogenous growth and blah, blah, blah in economics. For what concerns the standard deviation is 0.01, okay? Okay, so these are our data. If we look at the graph that we can create, you see that the red dots represent the random observations we have generated by sampling from a normal distribution with mean m and standard deviation s. The blue observations are conversely the true observations. So one thing that should strike our attention is that while for most observations somehow the red dots and the blue lines are compatible, there are still many situations like here, like here, like here, like here mainly, in which the normally distributed random variable with mean m and standard deviation s, because of the fact that the tail of the normal distribution decay very quickly and they close down, and we know that the probability of observing observation that is larger than 4 sigma in absolute terms is essentially 0 in practical terms. What do we have? We have that normality underestimates the large deviations that, on the contrary, we observe in the data. So using normality underestimates the tail. Now, in the next classes, when we consider extreme value theory, we will go into more detail, but you can already see the fact here. So you see that the red dots are always around here, and sometimes you observe some deviations that are a little bit far away from the rest, also under normality, but always nothing with respect to the actual deviations that you see in real data. So no single red dot reaches this value, or even these values here. Okay? So normality, we can already tell, underestimates risk in real data. Let's perform one simple exercise. Let's compute the 99% empirical valid risk of our data set. So as before, we compute the quantile at the 99% confidence level of our losses, and what we get is a value of 0.03. We also compute what is, under normality, the 99% valid risk of a normal distribution with the same mean m as losses and the same standard deviation s as the standard deviation of losses. And we see that this value is 0.025. So already at a very simple inspection that we can have by comparing these two values, we see that there is clearly a difference in terms of valid risk. So the normal valid risk tends to underestimate the actual empirical valid risk. For what concerns the expected shortfall, the first one, the empirical one, can be computed as before. For what concerns the expected shortfall under normality, we can apply the formula that I showed you before, that is this one. Okay, so we can just rewrite this formula to have the theoretical expected shortfall under normality, and this is the value that we get. Also, for the expected shortfall, we see that the expected shortfall that we can estimate empirically from the data is definitely larger than the one that we get theoretically from the normal distribution. And please observe, I'm always considering a normal distribution with the same mean and the same standard deviation as those of the empirical data. Now, let's try to backtest very quickly the valid risk. At a very quick inspection of the values, we can already say that the normal valid risk underestimates. So I corrected in real time. So the normal valid risk underestimates the actual valid risk, but we want to be rigorous, so we want to perform a statistical test. To perform the statistical test, we can use a backtesting procedure as the one that we have quickly considered in our class. So what we can do, we can fix a significance level for the test. So let's say that we use 5%, quite standard significance level. You may want to use 10%, 1% is your choice, or the one of the regulator. Now, what we can do, we can look at how many observations should be above the 99% valid risk. In terms of our data, we expect, given the number of observations that we have, we expect to observe 26 exceptions. In our data, conversely, we observe, because this is just 1%, okay? And in our data, conversely, with respect to the exceptions that we observe under normality, these are 74, okay? So if we assume that our data actually follow a normally distributed random variable with mean m and standard deviation s, then the valid risk under normality is the quantity that we have already computed before, and then we look at how many exceptions, real data, offer with respect to the threshold of the normal valid risk. And we find that there are 74 exceptions. Now we have that we expect, under the assumption that our normal valid risk is correct, we expect 26 exceptions and we observe 74. Now 26 is smaller than 74, so we are possibly underestimating our valid risk under normality. So given our significance level of 5%, then we have to perform a right tail test because, I repeat, under the test for underestimation, the test is a right tail test. Under overestimation, conversely, is a left tail test for the binomial distribution because we have this independence assumption and then we have these Bernoulli trials that we are considering leading towards a binomial distributed random variable. Now, what happens? We consider our right tail test, so it's 1 minus the CDF of a binomially distributed random variable computed in the value 73. Why 73 and not 74? Because we want the probability to be 74 or more. The probability of being 74 or more is 1 minus the probability of being 73 or less. Why? Because we are considering discrete observations. So between 73 and 74 there is nothing. That's why we have to always consider one observation less when we move to the right tail. Now, if we fix a significance level of 5%, which is a quite standard significance level, so if you want is the type 1 error in our test, so the alpha level, I don't know how you call that, but these are common names. If we set a 5% significance level for the test, but you can choose 10%, 1%, depending on your preferences, on how precise you want to be, or maybe it is imposed by the regulator, so there are some requirements prescribed by the regulator. If we compute this p-value, we get that this p-value is 0 followed by many, many zeros and 9. So at the end of the day is a 0. And compared with our significance level of 5% or any other level you may want to consider, we have that we have to reject our null hypothesis, that is to say that our normal valid risk is correct. So we have to reject our normal valid risk. And this means that, as obvious, already considering this plot as somehow obvious, given this very naive comparison, our normal valid risk underestimates the tail. So you can imagine that if you are using that valid risk in your capital requirement computations, probably you end up with a capital that is not at all sufficient to hedge the type of loss that you want to hedge, because you are underestimating risk. Okay, that was it for our second lesson. I hope you enjoyed it. Now, in next lesson, we will enter into a realm, into a kingdom that I like a lot, that is to say the world of extremes. We will start speaking about extreme value theory and extreme value statistics to try to understand how to model maxima and minima that are the possible sources of the losses we don't want to see in our portfolio.